Go live. Okay. Zoom. Transcript. Share. Oh. Ay! Ano nangyari dito? Bakit naka-duplicate slideshow ito? Hello, sound check. Hello, sound check. Hello, sir. Good morning.
Ay.
Sineset up ko pa sir yung ano eh. Ano ba to yung sa live streaming?
Okay.
Ang busisi pala nito.
Nakabukas na rin si Dean.
Mababa daw yung ano tawag dito. With streaming current bitrate is lower than the recommended bitrate. We recommend that you use ay ano ba yung ano ko ba naman ay well
Nasaan
tinry
ka ba
ko
ngayon? Nasa office ka ba, Vic?
nasa bahay sir kasi may sakit ako sir eh. Ewan ko ba. Hindi mo wala yung ubo ko. Kahapon nga, last week nga napilitan ako mag-schedule ng ano, remote class eh, instead of face-to-face. Gawa ng ubo. Ko ba naman? Ay, dito na pala si Dean. Hello po, Dean, nag-visit.
Hi, good morning, Sir Hill, Sir Vic. Napaaga ako napasok kasi sabi kasi Ate Lori, Sir, kailangan daw mag-register. Hindi, kaya sinubukan ko yung Zoom link. So, yon. Kaya napaaga ako. Go ahead, practice lang kayo.
Sige po, sir.
Okay.
Ano lang po yung registration, sir, para sa attendance. Nire-require kasi ng OVICRE.
Okay. Sige, dito lang.
Sige po, sir.
Hello, Dean. Good morning po.
Good morning, Sir Hill. Mamayang hapon pa tayo, di ba?
Opo.
Okay.
Pasensya na po kung maghapon kayo nakano sa...
No problem. No problem. Kala ko nga F to F eh. Andari naman tayo F to F. Mabuti na lang at least ngayon makakapag-multitask ka na kahit paano.
And I-share ko sa inyo yung message ni Dr. Rosario para...
Okay. Sige, sir.
Ma-view na rin ninyo.
Okay.
Eh? Okay lang. Okay lang.
Hello, good morning. Sophie, maybe we can start.
Good morning, everyone.
Hello. Kaya nanggagaling yan.
Good morning, everyone. So I am Sofia Lalisibuya. I am your facilitator for today's program. I would like to welcome everyone to the Centennial Professorial Chair Lecture from one of our faculty from the Division of Soil Science. So we would like to start our program with a prayer followed by the national.
Hello. Can you hear me?
Yes po, sir. Mali.
Okay. So everybody, let's start off with a prayer. So dear Lord, we thank you for this wonderful day that you've given us. Thank you for the strength. Thank you for the guidance. Thank you for the provision. And most of all, I thank you, Lord, for all of the guests who are here today, who have logged in and will be spending time to hear this lecture, Lord. And I pray, Lord, that they may be enlightened with the possible applications of my research to their specific fields and to their lives. Most especially, Lord, we pray for the students, the faculty, and staff of the university, that you give them good health and guidance, and also that you provide them with the driving force to serve the Filipino people. And we pray for the university, Lord. May the University of the Philippines be a beacon of light in the darkness that surrounds us. And most of all, Lord, we also pray for our country, Lord, that you instill the fear of God among our leaders, Lord, so that our country will be guided, Lord, so that we will honor you and so that we will be prosperous. We ask all of these things in Jesus' name. Amen.
Awitin po natin ang pambansang awit ng Pilipinas. Bayang magiliw, perlas ang silanganan, alam ng puso, sa titik mo'y buhay. Lupang hinirang, duyan ka ng magiting, sa manlulupit, di ka pa sisigil, sa dagat at bundok, sa simoy at sa langit mong paghaw. May nilang ang tula at awit sa paglayang minamahal. Ang kisap ng watawat mo'y tagumpay na nagtitipid. Ang bituin at araw niya kailan pa may magdidilim. Lupa ng araw ng maraming pagsinta, buhay ay langit sa liko. Aming ligaya na pag may mamapit at mamatay ng dahil sa'yo.
Yan. Thank you so much, everyone. So before we start, I would like to request everyone to please turn off your mic. Currently, we already have 50 participants and counting. To formally welcome us all, I would like to call on Dr. Villancio, the Director of the Agricultural Systems Institute.
Great. Thank you, Sophia. And of course, magandang umaga po sa ating Vice Chancellor, Dr. Jean Loyola, sa atin pong dekano ng College of Agriculture and Food Science, Dean Elpidio Agbisit, and of course our former director sa Agricultural Systems Institute and who are still active in this field, si Dr. Ed Panimbatan, nandiyan po siya sa atin, he's with us. And I believe siya yung advisor ni Vic Bato before, no? And of course, andyan po si Dr. Patrick Rocamora, siya po yung head ng Division of Soil Science. Sa mga mag-aaral na naririto ngayon at nakikilahok sa gagawing pagtalakay ni Dr. Bato sa kanyang Professorial Chair lecture. Ganun din po sa ating mga kasama sa larangan ng agrikultura. Again, magandang umaga po. And of course, this is to welcome everyone in this Professorial Chair lecture of Dr. Vic Bato under the UPLB Centennial Professorial Chair. No? So Dr. Bato is our Associate Professor here at the Agricultural Systems Institute. He got his MS in in Michigan State University, and of course in 2006, and has his PhD at UPLB in 2020. And of course, Dr. Bato is our expert in geography and land use systems, as well as in the geographic information systems and of course land use remote sensing and all those things. No? He was also associated, and I think with our project Sarai, still continuing right now. And all his work in the past 10 years, I think, is are put in this lecture. And with that, we congratulate, of course, Dr. Vic Bato for, despite the almost 3 years of pandemic that we have had, no? Yeah, 2.5 years actually. Not to overestimate it. All these things have been put into fruition, no? Yung kanyang professorial chair. Again, congratulations, Dr. Vic Bato, and welcome everyone for this lecture. Magandang buhay sa lahat.
Thank you so much po, Dr. Villancio. Again, congratulations, Doc Vic. Moving on, please welcome the Dean of the College of Agriculture and Food Science, Dr. Elpidio Agbisid, for the opening message.
Hi, Sophia. Good morning. Do you hear me properly?
Yes po, sir. Loud and clear po.
Of course, to our hardworking Vice Chancellor, Vice Chancellor Jean Loyola, to former Chancellor Rex Cruz, I saw him in the Zoom space, to the Director of the Agriculture Systems Institute, Dr. Virgilio T. Villancio, to our lecturer, Associate Professor Victorino A. Bato, to the movers and builders of our agricultural industry, to all our guests, friends, partners, a pleasant morning to all. On behalf of the College of Agriculture and Food Science, I wish to congratulate Associate Professor Vic Bato for this UPLB Centennial Professorial Chair lecture entitled A Dynamic Model to Predict Soil Erosion and Runoff in a Watershed During a Super Typhoon. This Centennial Professorial Chair lecture is a good avenue to share the research findings of this study, which can help in adaptation and mitigation of climate change. We know that our country, the Philippines, and its agriculture sector is very vulnerable to the effects of environmental changes. So we should always be one step ahead and always be prepared, future ready to any change that may occur. Predicting soil erosion and runoff in watershed is a good measure since watershed are our sources of clean drinking water, and of course, it supports also the biodiversity. Soil erosion can cause pollution in the watershed, therefore affect us all. Knowing the dynamics in soil erosion and runoff can help us propose and implement procedures to protect our environment. To all our participants, may you learn a lot from this lecture and generate ideas on how to better protect our environment. To Associate Professor Bato, my commendation for this research and knowledge. To everyone, may all our dreams and aspirations come true. Hiraya, Manawari, and good morning to everyone.
Thank you so much, Dr. Agbisit, for that message. Before we proceed with the highlight of today's program, again, I would like to request everyone to please turn off your microphone, especially during the discussion. Now, for the highlight of the program, please give a round of warm applause to our Professorial Chair Lecturer, Dr. Victorino A. Bato.
Hello, can you hear me?
Yes po, sir.
Okay, good. Thank you very much for coming. And at this point in time, I would like to acknowledge the presence of my advisor, Dr. Eduardo Panigbatan, who is currently logged in right now. Without him, all of this research would not be possible. So this has been possible because of him. So without further ado, let's begin. Hindi ko kasi makita yung controls ko. So the title of my topic is a dynamic model to predict soil erosion and runoff during a super typhoon in a watershed. So let's start with the introduction. The amount of eroded soil and runoff is a function of human activities, land use, and the amount of rainfall. The Philippines, being a tropical country with extreme rainfall events and highly erodible soils, soil erosion is a grave concern. That's what we have a lot here in our country. Lots of rainfall and highly erodible soils. So therefore, there is a need to develop a model that could predict or simulate soil erosion and runoff as triggered by rainstorm events in a watershed condition. Okay, excuse me, you have to forgive me. I still have this recurring cough. Such a model is needed to help in developing ways to protect the watershed from soil erosion and runoff, ensure clean water for the coming years, prevent or minimize flooding, and minimize siltation in rivers and dams. So the objectives of this research: to develop a dynamic simulation model that could predict soil loss and runoff in a watershed using GIS, remote sensing, and some related technologies. The specific objectives are to collect event-based rainfall data through installation of tipping bucket rain gauges with data logging capabilities in order to capture high-resolution rainfall data needed in the dynamic model. Second, to measure the water depth of the river using water height recorders with data logging capabilities in order to compare the actual river hydrograph with the simulated river hydrograph. Thirdly, to generate the land use, land cover data of watersheds through image classification of satellite data. Fourthly, to generate river hydrographs using rainfall data. And fifthly, to develop an optimized dynamic soil loss and runoff model. Sophie, malakas ba yung ano ko dyan, audio? Naririnig ba?
Yes po, sir.
Okay
Clear
lang?
po.
Okay.
Apo.
So let's first go to the theoretical framework. The amount of sediment removed and deposited in a land area, in case of a GIS, we have pixels, during erosive rainfall event is a function of the volume and velocity of surface runoff and the concentration of sediments this runoff carries. As the volume, velocity, and concentration of sediments increases, so does the amount of sediment deposition on rivers and dams during an erosive rainfall event. In a watershed, which is normally in 3 dimensions, we have the X, that's your longitude, the Y, the latitude, and the Z would be your elevation. In a GIS will be used in modeling to facilitate all overlay and map algebra. So what you're looking at right now on the left is the 3-dimensional image of the watershed. This is a limit watershed. And on the right, you have 4 maps here. The one on top is a digital elevation model. And the one on the right is the slope map. And the one below over here is the land use map, of course, with different types of land uses. And then over here, this white one, although you cannot see clearly, is the local drain directions map. I do have a zoomed in version of this map so that you can see it clearly later on. Now, I've used PC raster for this work. Probably a lot of you haven't heard of PC raster. It's been there for a long time. It's a bit obscure. Very few people use it. Probably you've heard about ArcGIS, MapInfo, what else? QGIS, but not PC raster. PC raster is a very special type of software. Why use PC raster? Because it's GIS based. It allows one to work at the equation level. It's quite easy to run, okay? PC raster has the ability to create this local drainage direction and move materials following this network in a dynamic manner. Without the LDD, it would be impossible to create this model. I think I have a picture of an LDD here. Okay, run. Yeah, okay. So this is the LDD, local drainage direction. And one thing that you might have noticed here, one thing that you should notice is that the local drainage direction follows the rivers and the tributaries. Essentially, this is where water will flow. Okay, this is where water will flow. And the one on the right, it's an animation. Yung animation, and someone's asking, about the YouTube channel, nasa program. Sophie, nasa program ang link. So I cannot post it right now because I'm in the middle of the lecture. So on the right, you will see an animation. It's an animation of the same watershed. And you can see that material, or let's say water, would be moving coming from the headwaters and converging towards this area here, this channel, which happens to be lower in elevation. So you can imagine not just water, but eroded material being carried along the LDD. This LDD and PC raster's ability to move materials through the LDD is what makes it special. ArcGIS cannot do this. Okay, even the latest version of ArcGIS cannot do this kind of dynamic modeling. Not even QGIS. Okay, so only PC raster. All right. And also, as I said, with PC raster, you can directly work at the equation level. That means you have to input the codes by yourself. And that's the beauty of it. You know what the software is doing, right? You're the ones who will be inputting the codes. You know how it's working. So this is a typical code for the model that I've developed. I won't go into detail into this, but I'll walk you through the three general parts. The bindings part, this is the variable declaration, okay, the variable declaration. And then you've got the initial part. This is the static portion of the model. And you see here the word dynamic. This is the dynamic portion of the model. You see that model is just about 50 lines of codes. It's not that very long. Okay. And as you can see, there are equations here where you actually input the numbers and input the maps, do your map algebra. So you're really in control of what's happening. You know what's happening. That's the beauty of it. So that's the theoretical framework. And moving on to the theoretical framework, the sediment loss per unit plane, we're talking about per pixel here, Q sub S, is in kilograms per second, is a product of sediment concentration and surface runoff. So that's Q sub S is equal to sediment concentration in kilograms per meter cube times Q, which is the surface discharge in meter cube per second. So don't worry if you don't get this math. I'll show you something much more interesting. I've got some pictures after this. Surface runoff discharge, Q, was computed using equation 2. This equation assumes that the channel is rectangular in shape, an assumption used in this model. So normally, river channels, they're not rectangular. They're ellipsoidal, mostly ellipsoidal. And it's hard to quantify an ellipsoidal surface. So we can simplify that by assuming that each of the channels are rectangular or square in shape. With that, we can use this equation. Q is equal to velocity times the height of the flow and times the width of the flow. So that's our Q. And then the velocity of surface runoff along these channels can be estimated using Manning's equation. So this is where Manning's equation comes in. And yes, I've inputted Manning's equation into that model. So V is the velocity in meters per second times this quantity, the hydraulic radius raised to the 2/3 times alpha, which is the slope in meters per meter, and N is Manning's surface roughness index. So these are these variables. During erosion events, the rills and the gullies form on the land surface. The rills and gullies are like channels that carry surface runoff and sediments downslope at a certain velocity. The creation of channels is a product of the entrainment process or the scouring effect of runoff. Manning's equation can be used to estimate surface runoff velocity. Furthermore, a uniform sloping surface in a landscape could be assumed as a very wide channel without sides. In such a case, the hydraulic radius becomes the height of flow. This is according to Hillel. Thus, equation 3 becomes equation 5. The velocity is now equal to h, which is the height of flow, times alpha, which is the slope, and n, which is Manning's surface roughness index. A Manning's roughness index may be generated by recoding the land use map. So this is where the land use map comes in. Each land use can be assigned a unique Manning's N value. And then here's another equation that I used. Rose equation. Your sediment concentration in kilograms per meter cube is equal to 2,700 times the slope times the eta, which is the efficiency of sediment entrainment, and C sub R, which is the fraction of soil uncovered by vegetation. C sub R can be estimated from the NDVI of Landsat 8. So this is where Landsat 8 comes in. And then entrainment efficiency, eta, can be evaluated from equation 7. Eta is efficiency of sediment entrainment. C is surface cover fraction. C, surface cover fraction, is contact cover in a strict sense, according to Rose, but can be estimated from NDVI of Landsat 8. Can be estimated from NDVI. So that's the good thing. Also, the soil fraction uncovered by vegetation, the quantity C is the contact cover. The fraction of the soil uncovered by vegetation, CR, was computed from equation 8. So CR is equal to 1 minus C, and CR is the fraction of soil uncovered by vegetation. C is surface cover fraction. So the erosion model conforms to the water balance equation in computing for the surface runoff of watersheds. The model also conforms to the law of conservation of mass. So runoff is equal to, so this is the water balance equation. Excuse me. Runoff is equal to precipitation minus infiltration minus evapotranspiration, where R is surface runoff, P is precipitation, I is infiltration, and E is evapotranspiration. But during erosive rainfall events, say it's raining so hard, these are normally the erosive rainfall events. Evapotranspiration can be ignored because its rate is very insignificant compared to rainfall intensity. Thus, in my model, the equation becomes surface runoff is equal to precipitation minus infiltration. So our equation has become much more simpler. Now, precipitation, we can easily measure this, or not so easy, but we can measure this using a rain gauge. And infiltration can also be measured because this is a soil property. Infiltration, by the way, let me define infiltration. Infiltration is the rate at which water enters the soil. Infiltration is highly dependent on time, soil moisture, and land use. During rainy seasons, the soil is already close to saturation because it's always been raining. And during rainstorm events, the soil is already saturated. And infiltration is already at its steady state or very close to the steady state, which is very close to the saturated hydraulic conductivity value of the soil. Now, the local drainage direction. Water moves from higher to lower elevation. Movement of material through the watershed follows the local drainage direction, or LDD. All sediments carried by water will travel until they reach a common point, or in the case of watersheds, the water level gauging station. So our common point here is the water level gauging station. So for example, this is our watershed, and this is on the right is a simplified version of it's a grid, okay, it's a raster. Let's assume that this is our digital elevation model. And this is now the arrow represents our LDD, and they will all converge to this point. This point is the lowest pixel in our digital elevation model. Of course, the digital elevation model would represent our watershed. So all materials will have to be coursed through this LDD and will end up here. And this is where we put our water level recorder. On our watershed, because I cannot show the LDD on the entire watershed, you won't be able to see it because it would all appear white. So I've zoomed in on one portion of the watershed that shows where all of the LDD converges. It's this point here. I don't know if you can see this dot, but this is the lowest point, the lowest portion of the watershed. Of course, there is still something below here. But this is where we've installed the water level recorder. As you can see, this is our watershed, and it's filled with the local drainage direction. And again, materials, water, sediments would somehow follow the local drainage direction until it gets here. Okay, before that, I hope you can somehow have an idea or view the watershed, have an idea of its elevation, okay? The blue color here, by the way, would be lowest in elevation, like 465, and followed by this one, which is, it's like camouflage, 591, and then the cyan would be around 843, and the red would be 969, and then this one would be 1095 meters above mean sea level. So this area here is higher in elevation. This is the lowest. So materials, water, and sediments would move here from a place of higher elevation, going down to a place lower in elevation where they will all gather and converge. Okay, I hope that's clear. So this was displayed in PC raster, the older version actually. Older version of the PC raster. The newer one, I've been having problem with the display. I don't know why. But it still works. The model still works. So, on to the land use and land cover. Land use and land cover is one of the major factors that influence soil erosion. Right? Land use and land cover, that's very important when it comes to soil erosion. Land use is directly related to surface roughness. The more trees that you have, the more vegetation that you have, the more rough the surface of the land is. Okay, the more rough the surface of the land is. Now, that's a good thing because if the land surface is rough, one of the principles in minimizing soil erosion is to increase the roughness of the surface. Why? Because it gives water enough time to infiltrate. Okay, a rougher surface cover of the land gives water enough time to infiltrate. Now imagine a smooth surface like an asphalt, and it's sloping. So if rainfall drops there, it would just keep on flowing with increasing velocity. But if your land surface is rough, the surface roughness would give rainfall enough time to infiltrate. Okay, I hope that's clear. Land use is directly related to surface roughness, thus can be recoded to create Manning's roughness index map of a watershed. Now, onto the basics of satellite remote sensing. The satellite captures digital image of the Earth's surface by recording the reflected energy from various surfaces in our planet. From the satellite data, the land use map of an area can be derived through image classification. Whether it's supervised or unsupervised, you can derive land use, land cover from a satellite data. In the model, the following land uses, land covers were identified from the satellite data: forest, brush, grassland, bare, rice field, and urban areas. And the Landsat data was complemented by the use of Google Maps. Because with Google Maps, excuse me, you can somehow directly identify the location of rice terraces. You know what? Rice terraces is some sort of an anomaly when you're doing modeling, because rice terraces are normally put in a, you can find them in high sloping areas, okay? In sloping areas, but then they're flat. So you have to somehow treat them separately, treat them with special care. So this is how it happens. You've got the satellite here that captures surface reflectance from the Earth. You have here the sun that radiates electromagnetic energy of various wavelengths, and it hits the Earth, okay, just like that. And whatever, it hits different surfaces of the Earth, bare soil, trees, leaves, and some of this wavelength gets reflected and goes back to the sensor of the satellite, and that's recorded. Okay, that's how it works. And this data is sent to the ground receiving station for pre-processing, and then for archiving, it is sent to the data center. Normally, it's the USGS. The raw satellite data can undergo classification using an image processing software. Land use, land cover affects infiltration. Yes, it does, because I have already tested this in the past, and I've got data for that as well. And then we've got the normalized difference vegetation index, NDVI. It's an index of the greenness of vegetation. High NDVI values means that the area is dense in vegetation and that the soil is totally covered by foliage. The NDVI values are proportional to surface cover fraction and could therefore be used in Rowe's equation. To compute for NDVI, NDVI is computed using this equation. NDVI is equal to near infrared band minus the red band over the near infrared band plus the red band. So you do this in a remote sensing software, or even you can do this directly in PC raster if you want to. Just simply input the equation and the maps involved. So just to give you an idea of my project site, so this is the Philippines here, okay, map of the Philippines. My project site is this one, Alimit River Subwatershed and Lagawe River Subwatershed. Okay, Alimit River Subwatershed and Lagawe River Subwatershed is just a small portion of the Magat watershed. This gray area here is the Magat watershed, and it's quite big. It's really big. In fact, majority of the province of Nueva Vizcaya is within or falls within the Magat watershed. But for my study area, Alimit subwatershed and the Gawe subwatershed, all of them falls within Ifugao province. So they're in Ifugao province. And of course, some small insignificant portions are falling within Mountain province, but most of them are within Ifugao province. And okay, this is Ifugao province. These are the watersheds. Adjoining provinces would be the province of Isabela, Nueva Vizcaya, Benguet, and of course, Mountain province. You will find the watersheds in the northern part of the Philippines. Okay, these are the coordinates. Now let's go to to do this research, you have to make use of rain gauges and water level recorders. And so we had to install them in our site. So this is the Lagawi River sub-watershed. It has an area of, so I have two sites, Lagawi River and Alimit River sub-watersheds. Lagawi River has an area of about 7,391 hectares. This is the boundary. I've installed, or we've rather installed, one rain gauge over here. Oh no, hindi pala. The rain gauge is here pala, here in Hingyon. This is the rain gauge. This is where we installed it, almost at the headwaters. And we've installed two water level recorder. One is here in the municipality of Hingyon, and one is here in Barangay Boliwang. Okay, two excuse me, water level recorders. And for Alimit River sub-watershed, the area is approximately around 25,478 hectares. We have a water level recorder here on this portion here, and the rain gauge is here, somewhere here in Barangay, this may Banawe area. Okay, just to give you an idea of how it looks like in the field. So this is our tipping bucket rain gauge installation installed in a Catholic church property in Barangay Poblacion, Hingyon Municipality, Ifugao. This is the rain gauge. It's rather small. So it's mounted on a GI pipe. Okay. The beauty of this, yes, it looks crude, but it does the job. The beauty of this, it's easy to service and it's affordable. Easy to service, just unmount the, sorry, not unmount it, tanggalin, remove the pipe from its, where it's installed, and then bring down the rain gauge, clean it up, because the rain gauge needs some cleaning up and servicing. Download the data and then put it back again. I guess the more expensive part of this is the rain gauge, because rain gauges are quite expensive. Now, whose idea is this, to mount this rain gauge like this? It's the idea of my advisor, Dr. Paningbatan. It was all his idea, so thanks to him. And this is how we install the water level recorder. It's encased in a PVC with holes. So PVC encasing of capacitive water level recorder installed in Lagawi River. River's riprap wall located in Barangay Boliwang, Lagawi Municipality, Ifugao Province. So this is where we installed it. And I think here's another view, but on a different area. This is Alimit River. And this is how it was installed along the riprap. Installation of water level recorder on a straight segment of Alimit River, Barangay Alimit, in Mayawyao Municipality, Ifugao Province. So this is the PVC pipe, and the PVC pipe has holes, and the water level recorder is inside the PVC pipe. Prior to the installation, we were thinking, how are we going to install that? We cannot simply imagine it. And again, these were all Dr. Paningbatan's idea, thanks to him. And after we've seen it installed, oh, suddenly it all makes sense now. So this is Dr. Paningbatan, my advisor, getting some soil. Oh, hindi pala si Dr. Paningbatan to, sorry. It's our driver pala. It's our driver getting some soil samples from the side of this area here. And some pictures of taken within Ifugao area. So this is how the watershed looks like. Some areas are still forested, good forest cover. Some areas are covered by grasses. Like this place here is covered by grass. Some areas are burned. They still do practice here, slash and burn. And we've asked them, why do you do that? Well, because it's easier. Remember, if you try to pull the grasses or pull the vegetation out or cut them it takes a lot of work. But if you just simply light up the grasses prior to planting, it's much easier. And that's how they do it. That's how they do it back there. So still, some areas have good forest cover. And look at this nicely laid out rice terraces here. Beautiful. And you look at the boundaries, the pilapil of the rice terraces. It's clean, it's nicely laid out, well maintained. And another view within Ifugao area, you see these nice rice terraces, and below them you've got here a river. The river here still has clean water, okay, and you still see a cluster of houses here. And look at the vegetation here, the forest cover vegetation. It's still good. People here know how to maintain good forest cover because they know that it's going to be their source of water for their rice field. So they know how to take care of it. And when we were doing field work, the only way to get around the area was through a motorcycle. And since I don't know how to ride the motorcycle, I had to have a driver with me. And even if you know how to ride the motorcycle, since you're not familiar with the place, it's better to have your driver. Now there's a little story here. I was riding on a motorcycle with my driver because the road was so rough and it was raining and the road was slippery and sloping. I was actually thought about it several times. I was forced to hug the driver lest I will fall from the back of the motorcycle. So asked the driver, Kuya, pwede ba kitang yapusin? And he agreed to that. So I had to hug him lest I will fall. At the end of the trip, I guess we became intimate. Okay. That's just a joke. The intimate thing is just a joke. Another snapshot in the area. Now, some areas are this steep. And yes, they're still planting some crops here. And as we know, this kind of slope would be very prone to soil erosion. And I don't really know of any kind of soil erosion practice that would be very effective in this kind of slope because it's just too steep. Okay, it's just too steep. I guess that for me, if you ask me, don't use this for agriculture. It's just too steep. Just let the grasses grow. But they keep on planting crops here. You'd be thinking, why? Well, I guess the reason for that is, let's say if this is the only land that you've inherited from your parents, what are you going to do with it? Well, you're going to plant something in order to survive. Sometimes it's a matter of survival. That's why people utilize these marginal areas for agriculture. And okay, this is a picture of the road that sometimes we had to travel. And okay, this is a photo of a traditional house, Ifugao traditional house. But as you can see, the roof is already non-traditional. It's already covered using a GI sheet, corrugated GI. And okay, these are also pictures of traditional Ifugao houses, but they don't use they use the GI sheet nowadays because it's much more durable. And it's set in the midst of this rice field. Isn't this beautiful? And okay, another picture from the area. These are rice terraces, just slightly above the riverbank. You might have noticed that they're planting along the natural levees that have formed. Yes, because this is where most soils get deposited. So this is where they plant rice. And to get to the other side, they have to pass through this hanging bridge. You see a lot of these hanging bridges in this area. What's this? Okay, another picture of the area. You see some the type of vegetation that they have here: grasses, and some forest cover. Okay, this is a landslide. This is very typical of some areas in Ifugao. The area is really very prone to landslide, especially during rainy season. So this is the time when we were doing field work and it's rainy season and our vehicle just couldn't get through here. And it's already a 4x4 vehicle that we rented because there's this landslide. It's blocking our way. So we just turned around because it's already unsafe. At least for us, it was unsafe. That's me wearing shorts, wearing the orange shirt. And just like any municipality in the Philippines, some municipalities in Ifugao also have a garbage problem. Somehow we ended up seeing in one corner, we turned around in one corner and we saw this. They have a waste management problem. And that's so sad, diba? It's a very nice place and they have a waste management problem. And this one is a sign, welcome Burnay Elementary School. And Burnay, Lagaw, Ifugao is 1 kilometer ahead. And if you want to go to the barangay Haol, this arrow is pointing up, meaning you have to climb a hill or a mountain to get to the barangay hall. And it's 100 meters, okay? You'll have to do some exercise here to get to the barangay hall. This is true, okay? This is true. So the water level recorder, water height recorder, and the rain gauge normally has a data logger. And this is how the data logger looks like. Well, the data logger is inside. This is just the waterproof casing. And if you open this up, you will find the data logger. Well, of course, the data logger has to be weatherproof. That's why it has this casing. So this is the opened waterproof casing exposed in the electronic components of the data logger connected to the computer via a serial to USB adapter. So this is your data logger. It's very small nowadays, and it's much more battery efficient than the older version. At this time when I was doing this, I was downloading the data. Okay. I think when I was downloading this, my wife was accompanying me in those adventures. So water and sediment sampling. Water samples were taken at the center of the river during perceived erosive rainfall events. The water samples were stored in a 350 milliliters polyethylene bottles and were brought to the laboratory for oven drying of the sediments. Of course, the date and the time of the water samples were taken were written there when the samples were taken. So since the place is so far from where I'm currently staying at here in Laguna, we had to ask people there to do the water sampling for us. So just told them, if you think that it's going to be raining strong, please get us some water samples. Of course, we paid for that. We paid for that. We had to pay the first people there for every sample bottle that the person gathered. And sometimes sampling is not easy, especially when it rains in the middle of the night. It's a bit dangerous. And we could easily slip and fall to the river, or you could be bitten by snakes. You know, we have a lot of poisonous snakes in the Philippines. So that's a constraint when it comes to sediment sampling. Now, once you've downloaded the data from the data logger, you have to sort through the data. Normally, this is a raw data from one of the loggers. If you download that, you'll get, for this one, it's 19,975 rows. And it has a it has a 2.5 months of data, worth 2.5 months. Okay. It has a 5-minute logging interval. So this is for the capacitive water level. It logs data, water height, on the river every 5 minutes. So it's it's almost close to real time because it logs data every 5 minutes. And so, yeah, it started, but oh, sorry, January, February, March, April, May 9, and ended July 17, 2015. So, yeah, lots of data there. And of course, how many water height recorders do I have? I think I have 3. And then you bring that to Microsoft Excel. You process that in Microsoft Excel. You clean it up a bit, modify the format, etc., so that it's compatible with your model as an input, okay? And then, of course, one of the things that you do in Microsoft Excel is that you graph that data. So you graph around 19,000 points of data starting from May 9 to putol pa pala to, May 31 pa to. I think this has been cut, but you can see here the changes in the height of the water in the river. So you have to sort through all of this data. Are you going to consider this? Probably not. I might consider this data because I might look at this event because water level rose from its current level, from its base height of about, this is meters, so let's say 0.8 meter. No, this is 0.2 meters. About this much. If this is 0.2, so let's say 1.5 or something. Oh, no, 0.2, let's say 0.1. Sabihin natin 0.1. From this much to this height, to 1.2, about 1.2 meters. So I'll have to look into this event. It's an erosive rainfall event because there's such an increase in water level height. And also this one as well. It might be worth looking at. So you have to sort through the data as well. And then after that, you also look at the rainfall data from the data logger of the rain gauge, raw data from the logger. Time of every bucket tip is recorded every time the bucket tips. It's a tipping bucket rain gauge. Every tip is 0.2 millimeters, and it records the date and the time. And this is the format of the data. As you can see, there are times or days when there isn't any rain, so you get a 0. And then another day is 0, and then another day is 0. And then this time you have 1 tip, 2nd, 3rd, 4th, 5th, and 6 tips and 7 tips. So for the tipping bucket rain gauge, the format is a bit not that consistent. So I had to fix this and had to make a customized program for fixing this. And again, you bring the data to Microsoft Excel, sort it out, and you graph it and see where rainfall intensity is high. It's high on this part. This is October 17, around October 17 to October 19. Okay. Rainfall intensity is quite high. So this is meters per 10 minutes. And let's go to the GIS data. So these are the digital elevation models of the 2 watersheds or sub-watersheds displayed in Aguila module of PC raster. This is Lagawe River sub-watershed and Alimit River sub-watershed. So the highest elevation in Lagawe River sub-watershed is around 1,480. Lowest is around 460 meters above mean sea level. For Alimit River sub-watershed, the highest elevation is around 1,200 meters above mean sea level, and the lowest would be around 350 meters above mean sea level. So you can compute for the slope map, and for the slope, for Lagawe River, the highest slope would be about 89%. And this one is a bit high as well, 1,007, more than 100% actually. 174% would be the highest in Alimit River. Would that be possible? Yes, that's possible. More than 100% slope. And for the Manning's N value, Manning's Roughness Index. So from the land use, I've used this by the way. For forest, 0.1, brush, 0.12, grass, 0.035, very thin grass, 0.03, bare, 0.025, river, 0.04, terraces, 0.06. Again, you have to pay special attention to the terraces because they're flat on a highly sloping land, trail 0.025, and the urban areas, which is rather insignificant but still had to be considered, 0.02. There are very few urban areas in that place. So after you recode your land use map, you can now, from the land use map, you recode it, you now have your Manning's Roughness Index map. So this is for Agawe River, this is for Alimit River. And then the saturated hydraulic conductivity. You can base the saturated hydraulic conductivity on the land use. So these are the values of KSAT in millimeters per hour for forest, 100.8 millimeters per hour, brush 42, grass 100, very thin grass 33, bare 0.6, river 0. So it's, let's assume it's 0 because it's saturated already. Terraces 6, trail 0.6, urban is 0.6. So take note of the forest here. It has a very high saturated hydraulic conductivity and also the grass. Okay, so once you recode the land use map to assume a saturated hydraulic conductivity value, you get these maps. So essentially, we're producing lots of maps here because it's GIS. That's what we do in GIS. And then the NDVI. So this is from satellite image classification. You might have noticed that the highest value is 94. Normally for the NDVI, you get some negative values, but then you have to do some, there's a term there, not rationalization. You have to not recode, but normalize. You have to normalize the data to somehow change its value from a range of 0 to 100. And let's look at some of the results. We have here the elevation map of Alimit River sub-watershed. Take note that elevation, mostly 74%, would be within the 500 to 1,000 meters above mean sea level. And above 1,000 meters, you have about 23%. For Alimit River sub-watershed, 61% of the land would be above 1,000 meters above mean sea level. Just to give you an idea, this would probably be much higher than Mount Makiling. Okay. And about 36% of the land would be between 500 to 1,000 meters above mean sea level. Yung 0 to 100, it's 0. There is no land in Alimit sub-watershed that's within 0 to 100 meters above mean sea level. Now for the slope, okay. Majority of the land in Lagawi River sub-watershed, around 34% of the land would be rolling to moderately steep. Around 32% would be steep. And only about 7.7% would be very steep. So majority would be steep. And for Alimit River sub-watershed, 47% would be greater than 50%. 31% would be 30 to 50%. So yeah, these are the distribution of the different slope classes. For land use, this one is interesting. Land cover, land use. As you can see, majority of the area in Lagawi River sub-watershed is still forested. More than half is still forested. Brush would occupy about 17%, and the rest would be grass, thin grass. The bear would be quite insignificant. The river would be quite small. The terraces occupies around 11.3% of the land in this area. So it really has to be accounted for. For Alimit River sub-watershed, surprisingly, 66% of the land is still forested. 12% is brush. Grasslands are about 4%, and terraces would be quite small compared to the overall area of the watershed. So let's look at the conceptual framework of soil erosion modeling. So these are the data that I used: slope, LDD, rainfall, water level, land use, NDVI, of course, rainfall. This goes to the soil erosion model, so soil erosion and runoff model. Now for the soil erosion and runoff model, you have two parts here. You have the surface runoff simulation part, and then you have the sediment concentration simulation part. And each of this sub-portion would have two steps. First step would be parameterization, followed by simulation. Parameterization and then simulation. And once I'm done with this, you have now the outputs: runoff, discharge, and sediment loss. So let's look at the outputs. So this is for Lower Lagawi River sub-watershed, measured and predicted hydrographs. So Lagawi River sub-watershed. So measured and predicted stream flow of Lower Lagawi River and rainfall intensity and depth. So this was for August 18, 2015. So below here, you've got rainfall intensity. So this is rainfall intensity in meters per second. And this is cumulative rainfall, the gray area. And for water depth, we've got here, the blue one is the measured water depth. Okay. And the black one is the predicted water depth. Okay. So the black one is the output of the model based on the various inputs, including rainfall. And how about sediment concentration? Lower Lagawi, or sediment mass, let's call it sediment mass, not concentration. Lower Lagawi River sub-watershed sediment mass and predicted hydrograph for August 18. So the blue one is the predicted water depth, and the brown one is the predicted sediment mass. It's sediment mass, not concentration. And the X's are those measured sediment samples. So, yeah. Now, moving on. This is for still Lower Lagawi. This time it's during the occurrence of Typhoon Lando. This makes it much more interesting. Typhoon Lando, or Kopu, the international name, which passed through the Philippines between October 14 to 21. So it was a very long rainstorm event. So let's look at the rainfall intensity. Yep, I got that. The data starts here, okay? It's been raining here on this portion, and then you've got this very strong rainfall here on this part, and followed by more strong rainfalls, and then it started to go down. So now this is the cumulative rainfall. And the measured water depth would be this one, the blue one. And the predicted water depth would be the black one. So water in Lower Lagawi River reached up to a height of 2 meters, maximum height of 2 meters during this time. So 2 meters can definitely carry an individual. That's going to be very strong. Can you imagine 2 meters of water raging through the river? How about the other one? I forgot to, this one, I'm sorry. The other one, it reached up to August 18, it reached up to around 1 point, let's say 6 meters. Still very high. Still very high. Okay, now let's look at the sediment mass in our runoff. So we've got here, the blue one is the predicted water depth, and the brown one is the predicted sediment mass, and the X would be the sediment samples. Unfortunately, the sample was only taken during the tail end, I guess because this is a typhoon. Who would want to go out next to a river and get water samples lest you be carried by the water? So see, those are some of the challenges when you're getting sediment samples. I guess one way to do this would be to do some automation so that you get samples at the peak of the storm. So let's summarize the data for Lower Lagawi River Subwatershed. We've got several rainstorm events, May 12 to 13. These are the significant ones, okay? I have to sort through all of the data. These are the ones that I found significant enough. May 12 to 13, May 30, August 18, September 10, October 18 to 19, and December 16. So in fact, I didn't put here this one, this one, this one, and this one. I only placed August 18 and August 18 to 19. October 18 to 19 is the COPU event. So let's just focus on this one because I guess this is the more interesting one. So total rainfall height is 68 millimeters. 68 millimeters, okay. Total rainfall volume that fell within the watershed. So you can imagine how big the watershed is. That fell within that is around 5 million cubic meters. Estimated total surface runoff is around 422 cubic meters. And eroded sediments, the estimate is around 57,905 kilograms, or about, we can convert this to tons, around 58, excuse me, 1,000 tons for this, for the COPU rainstorm event. Now, moving on to the Alimit River subwatershed, the measured and predicted hydrograph for, this time it's only for Typhoon Lando or COPU. Again, the blue one is the measured based on the water height recorder, and the black one is the one predicted by our model. So during this time, the water level in Alimit River reached up to a height of about 2.5 meters. Have you seen how big Alimit River is? It's very big. It's really very big. It's like as wide as the South Expressway. And the water reaching this high. And let's look at rainfall intensity. There you go. You've got this one and this one. And this one, high rainfall intensity here, 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 and here. And this is now your cumulative rainfall. And what else? Let's look at the sediment mass that got eroded. Again, this is the actual water height on the river. This is the predicted sediment mass. And this time, so there were lots of sediment samples gathered for Alini. Sayang. Dami namang nakuha. So the summary table for Alimit River Subwatershed. So let's focus on this event, the Super Typhoon Kopu. Total rainfall height measured in that place is about 148 millimeters. So that's quite high. And total rainfall volume is around 37 million cubic meters that totally fell on the watershed. And estimated runoff is around, surface runoff, 3 million cubic meters. And estimated total eroded sediments around 429,746,000 kilograms of eroded sediments. So I also did some scenario modeling, running the model under various assumed conditions. For example, conditions, reforestation versus denudation. And then what if under these conditions, you have a typhoon Lando-like weather condition? So let's see. So what if there is, okay, reforestation and denudation. Typhoon Lando intensity under reforestation. That means, what do you mean by reforestation? Grasslands, bare areas, and brush were planted to trees. So there is reforestation. So with reforestation, you have an estimated total surface runoff of 391,000 metric cube of water. And the estimated total eroded sediments would be around 44,783,000 kilograms. Now, what if we have denudation? Let's say 90% of the existing forest areas converted to barren. Let's say people suddenly cut down the trees. Well, just for fun, it's a scenario. So the estimated total surface runoff would definitely increase twice, from 391,000 cubic meters to 661,000 cubic meters. And also, the estimated total eroded sediments would also increase to 129,878,000 kilograms. And this graph somehow tells that. So the graph here, this is the predicted water level. The black one means no change, as is the current condition. The green one is under reforestation. And the brown one is when the forested areas gets denuded. So when we denude, when we cut down the trees, there is an increased water level. Sorry, there is increased surface runoff that goes to the river. So what does that tell us? There's very little infiltration of rainfall. Most of the rainfall would flow as surface runoff and go to the river channels. This is the thing that what this graph tells us. How about for predicted eroded sediments? Okay, for no change, the black line, and then if we do some reforestation, as you can see, there will be a decrease in the eroded sediments in the river. But if we do deforestation, there is a very significant jump in the eroded sediments that somehow would end up in the river. There you go. So this is for Lower Lagawe. How about for Alimit River? Same scenario, Typhoon Lando intensity. Reforestation is the same thing. We do reforestation of grasslands, bare and brush areas. And there's an estimated total surface runoff of 2,336,000 metric cube of water, and an estimated total eroded sediments of around 267,000 metric tons for reforestation. Now, if we cut down the trees, what will happen? 90% of existing forest areas converted to barren. We have an increase in the estimated total surface runoff to 5,554,000 metric cube, and then a total estimated total eroded sediments of 100,000, 1 billion kilograms of sediments, eroded sediments. That's a lot. Okay. Now the graph tells us the same story. This is the predicted water level. Current situation is the black line. If we do reforestation, as you can see, the water level in the river goes down because there's a lot of rainwater that gets infiltrated. But if we cut down the trees, we do deforestation, look at the sudden increase, significant increase in the predicted water level in our rivers. And man, this is dangerous. It can even reach up to 8 meters. This is catastrophic flood, 8 meters. Reminds me of the situation in Marikina. They're always monitoring the water level there. So how about for predicted eroded sediments? So this is no change. And this is your reforestation, and this is the deforestation. There's a sudden jump in the amount of eroded sediments. And of course, if you have these things depositing in your river channels, what do you expect next that follows this? Flooding. You'll have flooding, definitely. Mudslides, everything. So, I've already published 3 papers regarding this model on ISI and Scopus journal articles, on model journal pala, okay. The latest one was published in GESAM using Rose and Manning's equation to spatially quantify soil erosion in Lagawi rivers of Watershed, Ifugao, Philippines. Published in GESAM. This is the hyperlink if you want access to the article. Authors are, I'm the main author, of course, my advisor, Dr. Paningbatan, Dr. Elia, Dr. Alcantara, Dr. Cruz, and Dr. Sanchez. And then there's another article published in ISAAS. By the way, GESAM is ISI. It's an ISI journal. Another article was published in ISAAS journal. ISAAS is Scopus. This time the authors are me and Dr. Paningbatan, a physically based model for simulating runoff of the Lagawi rivers of Watershed, Ifugao, Philippines. And the third one published also 2020 to, yeah, by me, modeling soil erosion and runoff for super typhoon event using PC raster, Journal of Maps. This journal is both ISI and Scopus indexed. And I've also submitted a 4th one in PASS. For the past 2 years, I haven't heard anything from them. I don't know if it will ever get published, but at least I've already published 3 papers. So I told my advisor when I was defending this, maybe we can publish about 3 to 4 papers about this research, because it's about 2 watersheds, actually 3. And I guess you can get a lot of papers from it. I was able to do 3, so I think that's good. Of course, with the help of Dr. Paningbatan. And I'll just show you the attached map that I submitted in the Journal of Maps. So this is a time series map for a limit subwatershed. You have the main map here. And you've got the graph here, the same graph that you've seen. I think this is I cannot see it. So this is rainfall. This is water level. And the blue line would correspond to the date this snapshot was taken. And this is for Typhoon Kopu. So again, then we'll scroll down. There you go. As you can see, there are lots of colors that you can see on the map. What does this mean? This is eroded sediments in kilograms. So the red one would be the highest, above 10,000 kilograms. And the blue one would be the lowest, about 1 to 10 kilograms. And as you're advancing along the rainfall event, eroded sediment increases. Also for this part here, it goes up. There you go. And okay, there you go. Let's try that again. So we start here. As you can see, it's already raining, but there's very little eroded sediments, at least. Still quite significant though. But when you reach this part, where after this intense rainfall occurred, you have a lot of eroded sediments already. But the water in the river hasn't yet reached its peak. Okay, it's still here. Once you reach the peak water level in the river, all of the eroded sediments here in the upper portions of the watershed would have already gone down onto the main river channel. That's why, if you look at this map, the main river channel here has a color of red, because eventually the eroded material will find their way here. It will be carried by water. And there you go. Eroded sediment goes down because, again, rainfall intensity is going down as well. And here, it goes up again because of this rainfall event. And there you go. Increasing further. But once you reach this peak water level, as you can see, all of the eroded sediments here have found their way into the main channel. And this is the only part where you find a lot of the eroded material. And there you go. And there you go. And special thanks, of course. This research wouldn't be possible with my advisor, Dr. Eduardo Paninbatan Jr. And also I'd like to thank some of my Dr. Elpidio Rosario and Dr. Season. Also Ms. Juby Rocamora, who have provided assistance during the course of the research. And also Ms. Irene Almendral, of course. Without her support, things would have been rather difficult. So thank you very much. That's the end of the lecture. Please don't forget to sign the attendance. I need your attendance it's required by the OBCAA. So I'll give it back to you, Sophie.
Okay po. Thank you so much, Dr. Bato. Again, congratulations po. Thank you so much for that very new, informative, and interesting discussion about soil erosion and runoff simulation model in a watershed. Currently, we have 79 Zoom attendees, and earlier we peaked with 95 Zoom attendees. We also have some viewers in the YouTube channel po. To proceed, we would like to call on the former UPLB Chancellor, Dr. Rex Victor O. Cruz, for the comments and suggestions po. Hello po, Dr. Cruz, Dr. Rex Cruz.
Hi, Sophie. Good morning. Good morning, everyone. Can you hear me?
Yes po, sir. Loud and clear po.
Okay, sige. Let me just get my notes. Pag medyo may konting ingay, pasensya na ha. Medyo mobile ako eh. Sandali lang ha. Kunin ko lang yung notes ko. Okay. Thank you very much for inviting me here, and greetings to Vice Chancellor Jean Loyola, to Dean Pid Sagbisid, to Director Gil Villancho, and to the rest of the participants. Good morning to all of you. And of course, to our professorial lecturer, Dr. Vic Bato. First of all, let me congratulate our professorial lecturer, Dr. Bato, for the excellent presentation as expected. And his paper today is a reflection of his scholarship when it comes to soil erosion. And of course, using GIS and remote sensing, which is his forte. Modeling is essential for research, management, and policy formulation. I think I have to emphasize that because here at UPLB, we don't have that much culture yet in using modeling and simulation as our common tools for understanding things. And there are many things that we have to understand, and that models can be used to facilitate such an understanding within a short period of time, and even with limited data sets that we have. And so what was just presented to us by Dr. Vic Bato is an example of how modeling can help us in making decisions in relation, for instance, to soil erosion, surface runoff, and flooding. These are phenomenon that you cannot simply estimate or measure, right away in a given short period of time, and that will give you also time to respond and make the necessary interventions so that you can, or we can, avoid the adverse impacts of these processes. But with modeling, as we have seen, in a short period of time and with limited data sets, the projections have been made, and that is the advantage of using models. And let's just hope that many will get into this. At the College of Forestry and Natural Resources, we have instituted, I think, 2 courses already, one in the graduate and undergraduate programs, a modeling course on natural resources and ecosystem management. Third point is that when we go into modeling, let's remember that this will entail long-term modeling or long-term monitoring of watersheds. I hope that even as I said, that modeling can help us in understanding things within a short period of time, and even with limited resources or limited data sets that we have. I hope that I did not give you the impression that we can now dispense with monitoring. In fact, what we need more of long-term monitoring if we want to take advantage and maximize the benefits that we can get from using models for understanding natural processes such as soil erosion and surface runoff. So modeling will not in any way justify that there is no longer a need for long-term monitoring of watersheds. My fourth point is that, and this is a small point, I just want to point this out. In the beginning of the paper of Vic, you mentioned about soil erosion being the movement of one soil particle from one place to a place of, in a lower elevation. I think strictly speaking, we know that erosion can take place by moving soil particles from one point to a higher elevation, and that can happen when you talk about, for instance, mechanically induced erosion or wind-induced erosion, or even gravity-induced erosion. Sometimes can actually lead to erosion where movement of soil particles is from lower elevation to higher elevation. But that's a small point. I just want to, I just want to point that out. But I do understand where Vic was coming from, and that is he was talking about surface runoff induced erosion, which is really or truly, an erosion where movement of soil particles is from higher elevation to lower elevation. To lower elevation, because that's the natural movement of water. And then my last point, just to give enough time also for other question, is that when we do scenarios, when we do simulation of, for instance, soil erosion and flood and even stream flow using scenarios such as reforestation and deforestation, I'm always wary and make sure that people understand where I'm coming from. And I think this is also what we have to make clear, sa paper ni Vic, and this is also what we need to clear in other paper similar to what Vic has done. That when we use the scenario of reforestation and deforestation, especially in relation to soil erosion and surface runoff, we have to make it clear that it's not an instantaneous effect, right? For instance, the scenario of deforestation and barrenness, it's not an instant transformation. It takes time. And the reason why I want to emphasize on this is because it can create an impression to many, especially the environmental advocates and even the policymakers, thinking about degradation or forest deforestation as something that instantly lead to degradation, and that has created a totally misinformed thinking about deforestation and even reforestation, because even reforestation, takes time before they actually produce the benefits that you can get out of it, such as in reducing sediment concentration and regulation of surface runoff. These are things that are not going to happen within a short period of time. Now, the reason again why I'm saying this is because, when people get hold of this type of information, they tend to use it in a way that is really wrong. Such as, for instance, when people see that degradation can increase erosion and can increase flood peaks, for instance, or stream flow, maximum stream flows, they tend to say already that, therefore, we should prohibit cutting of trees in the forest, assuming that when you cut the forest at that instant, barrenness is going to set in already. Okay, and the same is true for reforestation. When people say let's get into reforestation so that we can get the benefit of stream flow regulation and minimization of flood peaks, they think that we are okay already once we have launched the reforestation and once we have planted the seedlings. But people don't realize, and many don't realize, that it takes time. It takes time before the impacts, the beneficial impacts will set in. And that can create complacency, for instance, in relation to preparing flood events that can still take place even after planting trees. Even after planting trees, after so many years, even after 10 years, you don't get that instant effect of flood regulation. So that's just for me a caveat. No, we need to put into this type of scenarios, when we do modeling and simulation, particularly when we talk about the forest in watersheds, and hydrology, because that is such an important basis for making policy, making management that people use and often use incorrectly. But having said all of this, I'm not discounting the importance of modeling and what Vic did. I always say, and as I said in the beginning, this is an essential tool. And what Vic has done is to open up really our eyes that, again, modeling is something that we really need when we talk about natural resources management, especially in trying to understand long-term natural processes such as sedimentation, soil erosion, surface runoff, and flooding. So with that, I congratulate once again si Vic for this wonderful lecture, and I know that he will continue to do so in this type of research producing more information that will be useful for policy making and even management decision making. So thank you very much. Big congratulations.
Thank you very much, Dr. Cruz. Moving on, we would like to request our attendees if you have any questions or concerns or any inquiries about the topic, you may send them via the Zoom chat. Also, I would like to remind everyone to please don't forget to sign in the attendance posted on your screen. So, any questions and inquiries from our attendees? None daw po. Others may have question po.
Very clear ang lecture kasi. Kaya walang
Okay.
questions.
So currently po, we have 73 attendees po sa Zoom. Any question po and inquiries? So very intimidating din po kasi yung GIS na ginamit po ni Sir and other men.
Sophie.
Yes po, sir.
Dahil wala pang nagtatanong, let me quickly yung ask question to Vic
Okay po, sir.
Vic, yung Manning's N natin, yung coefficient natin na meron ka na bang nagawa before trying to validate kung anong adjustments that we need to make for Manning's equations in different situations, because I know that there has been little study concerning the adjustments of Manning's equations on the basis of empirical data sets.
Yung sa Manning's equation, what I did was, Dr. Paningbatan had a previous study, I think it was in Lantapan Watershed. So I lifted that value and made a little bit of adjustments to fit my model and also to fit the situation in the watersheds, because Lantapan, again, it's a different area. Ifugao is a different area, different characteristics. So that's what I did.
Yeah. Right. Pero kailangan siguro marami pang study din dito. Yan ang problema natin sa maraming models, sa maraming coefficients that we really need to validate sa ating local conditions. And this is where yung mga sinasabi ko kanina, yung long-term monitoring is really needed. If you want to understand yung mga behaviors ng mga coefficients of models developed in other countries.
Yes. So it's basic research, right?
yeah, exactly. Yeah. So, totoo yun.
Look for money for that.
Yeah.
Eh baka tanungin tayo kung anong 4-piece niyan yung mga application, or 6-piece ba yun? Lagi nilang tinatanong.
No, you can just lagi yun tinatanong but kaya natin yang i-justify.
Thank you so much po, Dr. Cruz. Any other question po? Ayan, sir, may question. Ay, sorry. Wala po palang question.
Hello.
Nagpapaalam po pala.
Hello.
Yes po,
Dr.
sir.
Paningbatan, may question.
I would like to contribute to that Manning's equation. It seems that I was the only one who did a basic research on this. As Habi said, ginawa ko ito sa Lantapan, Bukidnon with some of my students. And we did this with very sophisticated procedure and instrumentation. No? Gumamit kami ng mga flumes to really validate it. And including not only the Manning's equation, but also the infiltration rates. It's unfortunate na kakaunti lang ang research that is being devoted into this aspect. Yung lalong-lalo na sa Manning's equations. No? Thank you.
Good to hear from you, Doc. Kailangan siguro
Wala
gumawa
pa talaga.
tayo,
Ha?
kailangan siguro gumawa tayo ng replication ng mga ng study na yan in different watershed conditions.
Yeah. I agree with you, Doc. You see, model simulation are meant to be validated. So we will have to constantly do some validation, monitoring, look at the real situation. Kailangan talaga ito, no? Lalo nandiyan ka pa. Okay.
Wala, retired na rin ako, pero tayo pwedeng gumawa nito. We can develop proposal for this.
Yes, I'm willing to participate.
Yeah.
Oo. Pa rin tayo, yeah?
Yeah, andyan si Vic Si Vic ang ating
Yeah. At saka congratulations, Vic. Maganda yung iyong deliberation dito sa delivery ng iyong lecture, no? I can very well understand it now. yung ating ginawa noon, no? And that was, you see, we did this some more than 10 years ago, I guess. Kaya marami nang nagbago. Sana
Hindi
ay
naman, sir,
magpatuloy.
not naman 10 years. 2015.
2015,
15.
no. Yeah, but and we did this not yung funding nito hindi galing sa sa government funds, but from a private funds. Kaya kakaunti nga yung lalong-lalo na sa sediment concentration monitoring. Dapat sana kung mayroon yung automatic sediment concentration sampler, which I did that. I did that in Lantapan. Mayroon tayong mga instrument na ngayon, no? So kakaunti talaga yung points to really pin down yung validity ng ating ginawa, no? Ginawa sa Alimit at sa Lagawi River.
Thank you so much po, Dr. Paningbatan. Sorry to cut you off po. To proceed, we would like to call on Dr. Jean Oloyola for awarding of certificate.
Okay. Can you hear me?
Yes po, ma'am.
Okay. Thank you, Sophie. On a personal note, congratulations, Dr. Bato, and thank you for promoting mathematics and physics by incorporating them in your work. So let me read po the citation sa certificate. The University of the Philippines, Los Baños awards the UPLB Centennial Professorial Chair to Victorino A. Bato, Agricultural Systems Institute, College of Agriculture and Food Science, for his consistent, exemplary teaching and research performance in the fields of soil physics, land use, geography, geographic information systems, and remote sensing. This award is effective July 1, 2021 to June 30, 2022, given this 17th day of October 2022 at UP Los Baños College, Laguna, signed by our dear Chancellor Jose V. Camacho Jr. Congratulations, Dr. Bato.
Congratulations po, sir. Again, please give a warm round of applause, virtual applause to Dr. Bato. So, to formally...
Maraming salamat po,
Sophie,
ma'am.
kailangan natin ng picture, ha?
Ay, oo,
Opo,
picture.
To formally end po, we would like to call on Prof. Patrick M. Rocamora for the closing remarks. After po ng closing remarks, I would like to request everyone po to open our cam po.
Okay. Thank you, Sophie. Magandang umaga po sa kanilang lahat. Sa ngalan po ng Division of Soil Science, we would like to congratulate and thank Professor Vic Bato for the presentation, another milestone in the division. Bibihira po kasi yung mga nakaka-professorial chair sa ating mga kasama. I would like to welcome and thank my previous professors, Dr. Panimbatan and Dr. Rex Cruz, and also we would like to welcome Vice Chancellor Loyola, Dean Agbisit, and Director Villanson. So again, in behalf of the Division of Soil Science, we would like to congratulate Doc Bato for the presentation, and hopefully many more professors from the division will follow and also look at the performance and presentation of Dr. Bato as a platform for future, no? Ika nga ni Dr. Rex Cruz for the decision making and also for the different specializations of the division. So again, good afternoon. Thank you very much and padayon po sa ating lahat. Magandang umaga sa ating lahat at keep safe everybody. Thank you.
Thank you po. Ayun po, I would like to remind everyone to please don't forget to sign the attendance. So the link is also posted in the chat box. Again, picture po sana. Please open your camera for one picture po. Ay, three slides po ito. Okay po. One, first picture po. Okay. Second po na picture. 1, 2, 3. Last po. 1, 2, 3. Smile. Ayan, okay na po. Thank you po.
Vic, congratulations, Vic.
Bata pa pala si
Bye.
Dr. Bato.
Salamat.
Salamat po, sir. Salamat po, ma'am.
Bye-bye.
Bye.
Doc
Thank
Vic.
you. Bye-bye.
Yes po, still here. Salamat po. Salamat for attending.
Thank you po.
Congratulations, Vic.
Thank you po, sir.
Sige.
Salamat po sa comments.
Okay, sige. Thank you.
Okay. Ay, nako.
Sige, Doc.
Thank you. Ano yan?
On pa si sir.
Ha?
Ay, naku, sir. Naka-on pa kayo. I-end ko na ha. Kasi naka-on pa yung iba.
Pag